So recall from years 9 and 10 that a quadratic in its general form looks something like this. Ax squared plus bx plus c equals 0, where this coefficient a is called the leading coefficient. Leading coefficient. And if we set this leading coefficient or the coefficient of x squared to 1, so if a equals 1, then we have a monic quadratic. And otherwise, when a doesn't equal 1, we have a non-monic quadratic. Now, the general process for solving quadratic equations is to first factorize the quadratic expression and then to solve the factorized expression. And as you might recall from your previous years, there are 3 main methods to do so. Let's explore them one by one using examples. So, as a first example, we have a monic quadratic, x squared plus x minus 42 equals 0. And so, the first method involves considering true numbers. I like to call them m and n, which in this case will multiply to give me the constant negative 42, because this is a monic quadratic. And they add to give me the coefficient of x, which is positive 1. So after running through my factors of 42, I see that 7 and negative 6 satisfy both these conditions. And so I can factorize the left-hand side of my equation as x plus 7 times x minus 6 equals 0. And whenever we have a product of 2 terms equaling 0, we can say that any one of the terms must equal 0, which means that either x plus 7 equals 0 or x minus 6 equals 0. So from the first case, we'll have that x will equal minus 7. And from the second case, we'll have x equal positive 6. So that's our answer. Right? Moving on to a non-monic quadratic, we again are in search of 2 numbers denoted by m and n. But in this case, m and n multiply to give the product of the leading coefficient 2 and the constant 5. That is 2 times 5, or 10. And m and n add to give the coefficient of x, which in this case is 11. So after looking at the factor pairs of 10, I can see that 1 and 10 satisfy both these conditions. And so I'm going to use these to split my 11x as a sum of x and 10x. So my left-hand side of the equation becomes 2x squared plus x plus 10x plus 5, which still equals 0. Okay, and so now because I have 4 terms on the left-hand side, I can factorize it in pairs. So for my first pair, the common factor is an x. So I can take that out. And inside the brackets, I'll be left with 2x plus 1. And as for the second pair, my highest common factor is a 5. I'll pull that out. And inside the brackets, I'll again be left with 2x plus 1 equals 0. And now we can see that there's a common factor of 2x plus 1 on the left-hand side of the equation. So we can take that out. 2x plus 1 times the remaining terms, x plus 5 equals 0. Which means that I again have two cases. One where 2x plus 1 equals 0, and the other where x plus 5 equals 0. And so from my first case, I have that x equals -1 over 2, or -1/2. And from my second case, I have -5. So that's my answer. All right. Moving on to the next method, which is called completing the square. So in this method, we're essentially forcing a perfect square into a quadratic. And for that, we need to remember these two identities. One being the square of a sum, which expands to a squared plus 2ab plus b squared. And the second being the square of a difference, which expands to a squared minus 2ab plus b squared. So let's have a go at a couple of examples by completing the square. So first we have the quadratic x squared plus 12x minus 31 equals 0. It should be a plus. So in this case, what I'm going to do is I'm going to match the first identity, which is a squared plus 2ab plus b squared, using the first two terms of my quadratic, x squared plus 12x. Okay, so matching up the first two terms with my identity, I can see that a in this question corresponds to x. A is x. And so that means 2ab must be this 12x term. I already know that a is x, which means that 2b must be equal to 12, or b must equal 6. And so assuming that it is a perfect square, I can write this as x squared, or different color, x squared plus 12x, which is my 2ab, plus b squared, or 6 squared, which is 36. But in my original question, I don't have a 36, I have a 31. And so I'm going to adjust this 36 by taking off a 5. And now I'm back to the original question. The first three terms of this left-hand side are my perfect square. And so I can factorize this perfect square using the identity, in which case I'll get a plus b all squared, or in other words, x plus 6 all squared minus 5 equals 0. And so now I can just solve for x. So I can bring over the minus 5 to the other side, making it positive 5. So x plus 6 all squared equals 5. Taking the square root of both sides now, I have x plus 6 equals plus or minus square root of 5. And so therefore, x is either minus 6 minus square root of 5, or it is minus 6 plus square root of 5. That's the answer. All right. As another example for completing the square, let's now consider a non-monic quadratic. So in this case, while it appears to be non-monic at first glance, I can tell that there is a common factor of 4. So I'm going to divide each term by 4, and I'll get t squared plus 4 equals 8t. And now we have a monic. So in exams or in homework exercises, before you start thinking that it's non-monic, just check if there is a common factor that you can take out and make it monic again. Okay, and now let me move this 8t over to the left so it looks like a normal quadratic. Equals 0. And I'm just going to try and complete the square for this one. So in this case, I'll be using the second identity for a squared minus 2ab plus b squared. And so again, my a squared matches up with t squared, which means that my a equals t. My 8t should then correspond to 2ab, but I already know that a is t. So that means 8 corresponds to 2b, and so b must be 4. Okay, and now I can write out a perfect square using the values for a and b. So I'll have a squared or t squared minus 2ab or minus 8t plus b squared, which is 16. Okay, and now I'll adjust the 16 to get back my 4, which is in the original question. And so to do that, I just need to subtract 12. And that should get me back to my original question. Again, the first 3 terms on the left-hand side of my equation is a perfect square. And so I can factorize it using the identity as a minus b all squared, or in other words, t minus 4 all squared minus 12 equals 0. Okay, and now I can solve for this by pulling the minus 12 over to the right-hand side so that I have t minus 4 all squared equals 12, which means t minus 4 equals plus or minus square root of 12. And so t must be 4 plus or minus square root of 12. Okay, and that's my answer. All right, and the last way to solve quadratic equations is to use the quadratic formula. And the formula reads as follows. So let's try and use this formula to solve the equation 2x squared plus x minus 3 equals 0. Okay, similar to completing the square, I need to match this quadratic up with the general form. So I know what are my values for a, b, and c. Okay, so in this case, a corresponds to 2. B is the coefficient of x, so b equals 1. And c must be minus 3. Okay, I'll just write this out. A equals 2, b equals 1, and c equals minus 3. And now all I have to do is to plug in these 3 values into my quadratic formula. So I'll have x equals minus b, so minus 1, plus or minus b squared, so that's 1 squared, minus 4ac, so that's minus 4 times 2 times -3 all over 2a. So 2 times 2. Okay, so I can simplify this now, and I'll get -1 plus or minus 5 over 4. And so my answer will be x equals -1 minus 5, which is -6 divided by 4, or -3 on 2. Or x can be -1 plus 5 over 4, or 5 minus 1 all over 4, which is equal to 1. And so that's my answer. All right. And as a last piece of content for this video, let's cover the discriminant. The discriminant is denoted by the Greek letter delta. And it's a very useful quantity when studying quadratics because it tells us the number of roots, and by roots I just mean solutions, or the values of x or whichever pronumeral the question uses, and the nature of roots. Okay, so with the discriminant, we have 3 possible cases. One where the discriminant is greater than 0, in which case the quadratic will have 2 real solutions. And when I mean real, what I mean by real is just a numeric solution to the equation. It could be a whole number, it could be a fraction, it could be a recurring decimal, but it just has to be a number, okay? And the second case is when I have the discriminant being equal to 0, in which case I'll have 1 unique real solution. And lastly, my third case is when the discriminant is negative, in which case I have no real solutions. If you ever decide to go and do extension 2 in year 12, then we'll be working on quadratics, which have a negative discriminant. And as you'll see then, these will actually lead to imaginary solutions. All right, so let's try and apply this in the context of an example. So here we have the question, find the values of k such that the equation kx squared plus 48x plus 64 equals 0 only has 1 real root. Okay, so the last part of this question about the 1 real root tells me that I need to consider the case when the discriminant is equal to 0. Okay, so let's see, what is the discriminant? The discriminant equals b squared minus 4ac. And by comparing this quadratic with the general form, ax squared plus bx plus c, I know my b is the coefficient of x, which is 48 squared minus 4 times a, the coefficient of x squared, which is k, times the constant c, which in this case is 64. Okay, and that must equal 0, which means that 48 squared, or 2,304, minus 4k times 64, or 256k, equals 0. Okay, and now I can just solve for k. So k must be equal to 2,304 over 256, which equals 9. So therefore, k equals 9. And that's my answer.